Good morning, everyone. I hope you've had a good rest, a well-deserved rest, and ready to continue. This is third, uh, the second lecture of the 3 lectures on machine learning. I'll briefly review what we saw on the topic of discriminative models, but we are transitioning to generative models, essentially implying that now we would be working with data that does not have labels. So you remember the XY pairs, our training data was essentially data that for which we had some data for which we knew what classes they corresponded to. And of course, that labeling happens in multiple different ways, sometimes in a supervised fashion and expert. But now, today, we're going to focus on a case where we don't have those labels. We just have the data itself. So the topics that I want to cover are, first, I want to talk a little bit about transition from supervised to unsupervised learning. And the 3 main topics that I want to talk about are what I would describe as fundamental conceptual building blocks for generative models. At the end, I will talk a little bit about variations or advancements on these building blocks, or how to use these building blocks to move closer to a lot of systems and practice that we're familiar with. Those building blocks, so the first one is what's known as a variational autoencoder. And the second one is a generative adversarial networks. And the third one is diffusion-based generative models. Now, the variational autoencoder and diffusion-based generative models, they operate on a similar principle that we have been evolving, which is the principle of essentially working with some optimization of the likelihood function. So we work with likelihood functions, whereas the generative adversarial networks operates directly on the underlying distribution of the data rather than its likelihood function. The reading material I'm going to include for each one of those topics separately. So let's start on the first topic. And we basically want to first start by being able to differentiate between discriminative and generative models. The 2 papers that are listed here, the first one, Kingma, is the original variational autoencoder paper. It's a 2014 paper. So as you can imagine, a lot of these ideas, even though to some of you who have come across them, they may seem that they've been here forever. They're relatively new, about a decade. But just because they've had such an impact, they have been consequential in so many systems, and there has been an explosion of work that have built on these. That's why they may seem that they've been around longer than they have. If you look at, for example, that paper, I can't even tell you the number of citations that one has. Well, the author, not just on this paper, but has something over 300,000 citations, just to give you a sense of what the scale, the magnitude of what we're talking about. The second one, Carl Dorsch, that's a tutorial on variational autoencoder. It's for those of you, I recommend, for those of you who just want to start, not really digging into all of the details, but you just want to develop an understanding of underlying ideas, start with that tutorial. It's a nice tutorial. Okay, so let's recap what we did on Saturday, in the last lecture. So the idea of supervised learning was that we have a data set, let's call that D, that has a set which is indexed by I. I is essentially just a data point with its corresponding label. So for example, you have a time series or an image that you want to associate with a flare. And the simplest case, if it's a class, it's a binary class. It doesn't have to. Remember, last time we covered multi-class. But the simplest case is a binary decision, is there flare or not? So what this D means is that you look at the data that you have for which you already know that the answer, it's because you have verified it, past data, okay? And then you use this data, this pair of data, to be able to now design a predictor so that if new time series data comes, you will be able to make a decision on whether there will be flare or not, just based on the pattern that you have learned. And we spent the last lecture talking about different ways that we can build that predictor based on essentially doing ideas that have to do with minimizing the likelihood of some score function. We call that capital F. Okay, and that score function, the important point to keep in mind is that we progressively added complexity to the characteristics of that function. But the important point to remember is that the final one, which was the most general case where F was nonlinear, at the beginning it wasn't nonlinear, right? It was linear, and then it became linear in the weights or the parameters. And then finally, by the time we got to deep nets, we relaxed this to become a general nonlinear function. But they are all special cases of this. That's the important point that you should remember from the last time, okay? And so the examples that we covered were linear regression, logistic regression, support vector machines, and deep nets. And now we want to transition to what if we don't have labels? We have data, but we don't have any data for which we can actually assess. Is there a flare or is there no flare? Okay, so what does that mean? That means without labels, we only have this RD, the data set is just Xi's. So learning from the data itself, Xi's. And that's going to be the theme for today and tomorrow, with slight different variation on what I'll talk about, flavor. So the goal is a little bit more, I would say, ambiguous, maybe not as well defined as the discriminative model. But the idea is to recover hidden structure. And that's going to be the theme for today. The hidden structure, meaning that typically when we think about these high dimensional spaces, with data, a lot of times that data does not reside in an arbitrarily large high dimensional space because there is underlying structure in that data. So it resides in a lower dimensional space. And our goal is to find that lower dimensional space, the goal of the algorithms we develop. Another theme, which is the theme that I'm going to talk about tomorrow under exploratory data analysis, is the idea of either dimensionality reduction or compression, finding the essential, let's say, vectors of directions in the data, patterns. For example, the problems, the tasks that you saw as examples that correspond to clustering, segmentation. Can you cluster the data just automatically with our eyes? We can do that in lower dimensional cases, right? Two-dimensional, you look at some scatter plot, maybe we can scatter it. But if it's in 1,000-dimensional space, we can't do that. You go past 3 dimensions, it becomes hard to visualize these things. So we want to be able to automate that. And that's a topic we'll talk about tomorrow. Explore or explain data, and that means essentially generate data. And there will be many applications, as you can imagine. All of the generative models in which images are generated, text is generated, answers are generated to the questions that you would ask. All of that has to do with essentially generating new data. And sometimes, and this is a question that was asked last time, about what about the labels? How do we generate labels, and what are the issues for generating labels? And this also is used in many contexts for actually generating labeled data. If we can, for example, find clusters, we can actually assign those labels. If we trust those, if we can do that in a robust way, now we generate labeled data. Okay, so first of all, why model a distribution P of X? I'm saying modeling a distribution P of X because that's a fundamental departure from what we did last time. In the past, we were essentially working with a likelihood function of the data given the class, okay, and because we had the pairs. But now it's just the data itself, so we have to either work with the distribution or some function of that distribution, maybe moments of that distribution. Okay, I already talked about that. This is the category of the 2 things I'm going to talk about today and tomorrow. The first 3 are the topics I'm going to talk about today. Variational autoencoders, generative adversarial nets, score-based generative models, or diffusion model, or diffusion-based models. This is the most recent version of generative models. It's been around only for less than 5 years. And then tomorrow, I'll talk about principal component analysis, K-means, Gaussian mixture models, expectation maximization as methods for automatically find patterns and structure in the data. Okay, so far, what have we done? We have done maximum likelihood, and the typical model, which I said in words, you can see now, is working with a conditional density, so probability of the label given the data. And as we saw last time, we essentially have this general nonlinear score function, f, and the details of that depend on the specific technique or method. And then you remember this when we talked about multi-class. We had the binomial distribution, and we had this normalization. The normalization essentially guarantees that we will have a proper probability density function. The values will be between 0 and 1. You integrate the function, you get 1. So that's essentially, those are the requirements, okay? And this is what's known as the normalization factor. And now we want to model the distribution X, okay. So given data points X, how can we model? The maximum likelihood approach, in this case, notice there's no label in this case, there's no Y. And the idea is the following. We have the set of parameters, we call these set of optimal parameters. And we want to maximize with respect to those parameters. I mean, theta is a vector set of parameters. Maximize essentially log of that likelihood. But notice the form of likelihood is that it's probability of the data samples given those parameters. So essentially that means a search over parameters that maximizes the likelihood of the data. It gives you the essentially the most likely function based on some observed data. So that now, if new data comes, essentially you will mimic that underlying distribution. That's the idea. So you can draw from that. The simplest form is, which is what we're going to talk about, is for example, if you can model this parameter as Gaussian, then meaning that likelihood is Gaussian. What are the parameters of that Gaussian? What is theta in that case? How many parameters do we need to define a unique Gaussian distribution? Yes, exactly. So you need the mean, you need the variance, and of course the energy of that. And so that's the set of parameters. Now, so our goal in that case becomes find those parameters theta, so that you max your Gaussian essentially explains the data that you're working with, the data that you're pulling. Did you have a question? It means that it's essentially it is with respect, it's a joint. Basically, the variable of this probability density function is X, but it's based on, it varies based on theta, right? So it is, for example, in the case of Gaussian, that probability density function is going to be a Gaussian, but the parameters, the shape of it will change depending on what theta is. No, you have one, but it changes with theta, right? So if you change that's right. That's why theta is a variable. That's why you can search over those parameters. And every time you change those parameters, you still get a Gaussian no matter what those variables are, because the underlying structure is still a Gaussian, but the width, the distribution, the center, the mean, and the spread gets changed based on theta. So in other words, the only thing we are searching is those parameters in our fit. That's basically what we're talking about. But we are fitting to the data itself. There's no labels in this case. Okay, so this actually explicitly shows you what I was just explaining to you. In linear regression, what did we have? We had our conditional probability or likelihood function was probability of each class given that data. Okay, that's because we had our data set D was a pair of X and Y's. So we could use that. It's the Gaussian, right? With such that we had this W was the weight multiplied by a function or a feature, for example, a polynomial or a Gaussian, a polynomial of X. Okay. In the case of generative, this maybe explains in more detail the question that you were asking. This slide, I should have gone to this directly. Probability of X given the parameters, either theta or W, we call those parameters. In this case, those are the main ones. And this is basically the reason why you don't have the energy is because you normalize, this is essentially you normalize to 1, right? It's a unit variance, zero mean unit variance. And so whatever sigma you end up with are deviations from that standard normal. And all we do is, in this case, you see there's absolutely no y. We're not finding the difference between y and projection of these parameters. All we are doing is that we are looking at the difference between each data point and the parameters that we want to choose. In this case, the shift or the mean and the variance. Okay. So that's the fundamental difference, conceptual difference. Okay, so more broadly, you remember that we work with the logs. So natural log of probability of theta of xi is the sum over some latent variable. Okay, I showed you probability of theta of some latent variable, something that we have no direct access to, we can't see, because we're only looking at the set of data that we have, right? We don't have the full distribution, remember that. We just have the data given to us. But that there are other variables that play a role in that underlying distribution that we don't have access to. So define that as a latent variable z. And in the case of discriminative, we're just looking at probability of y given x. Okay, that's the difference. We don't see the z's, latent variables, but we always see the labels in the labeled data, that pair that we have. Okay, so pay attention to that z, because that's going to be central in our discussion for the remainder of today. In particular, the first topic, which is the variational autoencoder, that becomes essential. So that's why I'm going to go through some conceptual examples first before we go through the derivations. Okay, suppose I give you this data, and suppose that I'm plotting x on this vertical axis, and I'm only showing you data for some second variable. I mean, data can be generated in many dimensions, right? Could be 1,000 dimensional. If you have 28 by 20 images, it's 784 dimensions for your data, right? And because each pixel can take different values, right? So suppose that I'm showing you this very simple two-dimensional case, and suppose that this is the data that you observe. You take data and you end up here. What would you do with that data? How would you model it? What would you say? Somebody gives you this data. Those are samples, each blue dot. What would you do with it? Yes. Yes. That's right. So basically, the data appears, and you say, okay, I have a data over here. I have another data over there, and it just lies in this range. If you want to model it, how would you model it? What would you model it as? What sort of, yeah? But probabilistically, what do you model it at? What sort of probability model? Because it's a distribution. We're talking about a distribution. You're drawing the idea, the conceptual idea, is that all of these data points come from an underlying distribution to which we have no access. But you're observing this. And so what do you do? What's a reasonable model for this? Gaussian, where the center may be somewhere in there, around here, and then you have some spread. That's your spread, right? That's fine. And you can see here, well, the red line gives it away. You can model it as, you don't have to model it as Gaussian. In fact, you can model it as uniform. Now, what about if you have these two clusters? You have some data you take, then what do you do? How do you model that? Two Gaussians, exactly. This is a topic we're going to talk about tomorrow at length, but it's basically a mixture of Gaussians, two Gaussians, okay? But what if now this thing, instead of two, you had just an entire line, straight line covering this, all blue all around here, from down here all the way up? Then what would you do? Yes? Yeah, you could do that. Again, it's one of those questions that doesn't have a fixed answer. You could model it as if you model it as a Gaussian with a wide spread, it doesn't really tell you much. You could model it as a uniform distribution. Again, that doesn't give you a lot of information. It may be true. But the idea is that if we had a different embedding of that distribution, if we had access to some other latent variables that generated that distribution, perhaps we could do something a bit more clever. So here's an example. Suppose instead of just that one point, I had only one point, one axis, right? This is the same thing that might spread up. But now, by having access to a latent space, that second dimension, now I can see that essentially each one of those is a Gaussian. There's a spread in this direction. There's a mean and a spread. But the underlying distribution it's just, you can see it as a line. It's just a line. But then it has Gaussian, essentially, densities all around that line. So the point that I'm making is that even though we looked at those dimensions, the structure is a simple line that underlying the structure. And of course, we can't see Z, so we can't see that magenta line ahead of time. But our goal, the entire goal of generative models is that, is there any way that from data directly we can uncover that magenta line in the simplest example that I'm showing you? Can we do that direct? So you're saying take the covariance, look at the principal components. You can do that with some restrictive assumptions because you still have some assumption of linearity. But what I'm trying to do here is to keep this as general as possible. I'm saying that I'll go over in more detail. Let's look at more examples, and I think it will become clear. Suppose you have this handwritten 7, okay? If you look at this handwritten 7, and if it's generated, this is the pixel, and suppose you have 784 pixels, okay? What that means is that even though your underlying space is large, that you have that many dimensions you have, those handwritten different 7s that people write with handwriting don't arbitrarily reside in that high dimensional space, 784. They reside in some local neighborhood, okay? And that's really the underlying idea behind this manifold hypothesis, which means that X is a high dimensional vector in general, but the data is concentrated around a low dimensional manifold, okay? So instead of just looking for all possible values that each one of these could take, what we really want to do is to find essentially the line through that structure. That's what we want to find. And we want to do it automatically. Why does it even make sense to do? This example, I think, is a useful one. So if there's one thing that I think I would like to stay in your mind from what we're talking about is this picture. What do we have? We have on the left, it's just a Gaussian. It's samples drawn from a Gaussian, right? So basically you have a Gaussian. This is the center in 2 dimensions, right? So you have a spread on both dimensions. And that's your spread, that's your mean. But what are we looking on the right? On the right, we're looking at actual transformation, a mapping that shows you not a Gaussian, but something with a structure, this ring. In particular, the particular mapping that if you map each point here to this space is the following. It's an expression that looks like this G of Z, okay? In other words, your data may have structure if we were privy to that underlying latent variable. In other words, if we knew what G of Z was, we would be able to find that structure. Of course, we don't know what G of Z is. And the goal of generative machine learning, in particular, starting with variational autoencoders, is to learn this function G of Z. And you have heard, of course, yesterday, on Saturday in the morning, when I described deep nets as a function approximator, and then later on you saw some examples of that. That's the idea. If we can utilize what we already had as a function approximator and learn this function G, then we would be able to essentially unveil the structure that's in the data. Okay, that's the underlying idea. Let me pause. This is really at the heart of what I want to talk about. The rest is just going through the intermediate steps for the derivation. But conceptually, this is very important. Are there any questions? Yeah. Yes. Exactly. Exactly. That's right. We want to find out this mapping because this essentially the transformation into that the new variable is what gives us the structure of that distribution that we want to recognize, a pattern that we want to recognize. Yes. Oh, that's a good question. You're saying, so in this case, we only have one Gaussian, right? Now, if I change my Gaussian, maybe the cluster would move somewhere else if my mean changed. And maybe the spread, it will be more concentrated for a lower variance or bigger spread for larger variance. But nonetheless, this mapping would still give you a ring with different, the attributes of that ring would change. So in other words, you still get that mapping. It will give you a ring because as long as you have a Gaussian, okay? But the attributes of that ring will change. Okay, yes. Yes, yes, absolutely. Both of these questions are very important for clarifying the central point. That is, both of those are right. In other words, notice that we're in fact, part of the way we're going to set up this problem of variational autoencoder is to draw from a distribution with varying the parameters of that distribution. So you change the parameters of that distribution, and we don't know a priori what that function g is. This g would give you a ring, but any other g would give you a different set of patterns. And the whole point is that the data in X will give us that information if we can learn that latent variable z, which is the argument of that function. The function g can be anything. That's the answer. But we want to learn that. That's what we're going to do. Yes. Absolutely. Exactly. In words, the manifold hypothesis states that even though our representation, for example, images, may reside, we're defining it in a high dimensional space, the data that we take has structure that is the low dimensional space. It resides in a low dimensional space. And our task is to find that low dimensional space. Yes, that's one example of it. Yes. I'll show you some examples, in fact. I think that might be even the next one. Okay, so we have this is an example of, now it actually illustrates exactly the discussion that we had in the last few minutes. Suppose z, that random variable, is defined over an interval 0 to 1. Okay, now if I were to just draw those values, I would get maybe this, if I look at the probability with respect to theta of these two dimensions, x1 and x2, I would get this number 6, right? But if it's conditioned over that latent variable z, if I recognize that that's where it came from, then I would essentially find that this is the mean of z. The mean of z is the magenta line. And then I know that essentially I have a distribution around the mean of that latent variable. Okay, that's the task. Let me show you another example. This is a picture from the original 2014 paper. What you're looking at here is a set of images, a whole bunch of images. And the two dimensions, so they use two-dimensional latent variables, z1 and z2. Okay, and on the left, what you're looking at is a set of images where in the direction of z1, the orientation of the face changes. So the face goes like this. Okay. In the direction of z2, the expression of the face changes, maybe from happy or smiling to not being so happy. So that's how it changes over here. But the point that I want to make here is that they did not assume this or sort it. The data, the algorithm, variational autoencoder, obtained these two latent variables from a whole bunch of set of images. So it essentially obtained these two dimensions automatically. The same thing is over here. These are handwritten numbers. So this is for text recognition, for example, handwritten text recognition. And what changes here is essentially the orientation of these handwritten text. And what changes in this direction is the style, different ways of writing these texts. And the architecture that I'm about to describe to you automatically identifies these two latent variables in your images. Okay. So let's talk about now the building blocks. Given Z, we can generate, compute, or sample data X. And the idea is that Z from simple Gaussian and transformation via deep net gives us something that's known as half of the building block of a variational autoencoder. It's called the decoder. And the decoder architecture is essentially no different than what I described so far. You have an underlying Z, say if the simplest case it's a Gaussian. You draw samples from that Gaussian, and then you learn based on this function approximation architecture, underlying architecture using deep nets, the samples of your underlying distribution. You draw X1 and X2. Okay. Now, here, you can look that more generally, if this is a Gaussian, as an example, you draw samples, and then you end up with something that looks like this. Of course, as you were asking, there has to be one particular mapping that gives you, where you map the points over here and you get there. But the idea is that that mapping is given by the data, the xi's that we have. And it may change when xi's change. But you want to learn that from the data that's given to you automatically. Okay? So the question is how to optimize for theta. How do we know which z maps to which x, which is really at the heart of the question of what we're talking about. How do we know this mapping? How do we learn that mapping? Well, let me just go through a little bit of derivation, and I'll tell you what the essence of this is. We want to maximize probability of x with respect to that parameter theta, okay? Given a data set, a set of data points xi's, we have n of them. And this really means the probability of x with respect to those parameters, theta, for example, parameters of a Gaussian. And that means that that optimal theta that gives us the best fit, the mapping from that cone, the Gaussian, to number 7, we just have to maximize that probability, underlying probability. But what is that underlying probability? If you just write it out as the law of total probability, it's the product of x given that latent variable z that we don't observe times probability of z, and you integrate, it's like a marginal, you integrate with respect to z. Okay? But the problem is, how do we compute this probability of x given z? Remember, the simplest case, in fact, that's the building block for a variational autoencoder. Z is a Gaussian. So if you want to draw samples from a Gaussian, you need a lot of sampling, which I've written over here. You need a large N to actually do this sampling of the data. Okay? It may be not traceable. So the idea behind a variational autoencoder is just don't randomly sample from that distribution. First, generate the more likely z's, and then use those more likely z's to learn the mapping. Okay? Let me say that again. The idea is not to just compute this by just standard Monte Carlo sampling techniques, but first generate these z's that are more likely to have come from that data, and then perform exactly that function approximation that we talked about. Okay, so how do we do that? And that takes us to the idea of the overall structure of variational autoencoder. What I have shown you so far is the decoder part, which is basically given by the probability with respect to theta, parameters of x given z. In other words, if we have z, if z is some Gaussian, I can then draw samples x from that distribution. This block here is what's known as the encoder. And what that means is that if I start with z given x, x is my sample data, right? That's what I'm learning on. So I have access to x. I don't have access to z. Then I can generate perhaps learn the more likely z's, which then can be used by the decoder. Okay, that's the underlying idea. So what is p sub theta of z given x? What is the encoder block? Well, I'll just write it in the equivalent Bayes theorem form. Okay, and then the numerator is the same. P theta of x is the distribution, and this is exactly goes back to what I was talking about, the normalization factor, which is hard to attain. Okay, and that I already mentioned, sampling techniques are costly. We have to approximate this p with another surrogate distribution, which is parameterized by these parameters phi. We call that the encoder. Okay. All right. So the encoder is, again, another deep net. It's another function approximation that we have. But what is at the input is the sample data that we are learning on. This is the only thing we have by which we want to learn the underlying distribution that generated these. Okay, we have these x's. And the idea is that this conditional distribution through what we are learning over here is essentially a something that generates Gaussians. So this is, by the way, a recurring theme when I talk about the diffusion model, because the idea there is also to generate noise and then come back from noise to the structure. Okay, so we can parameterize this, for example, with a mean and a variance if the underlying assumption is that this is a normal distribution. Z is a normal distribution with mean given by mean of x, and the standard deviation given by the standard deviation of the data that we are learning from. Notice that instead of standard deviation, I've put log of sigma squared. That's just to guarantee that this is a proper standard deviation, so that it guarantees that it's positive, essentially. Okay. And now this is the combined overall structure, where essentially we have the encoder block generating z, and the decoder block from z generating samples of x. Okay, and remember, this is being learned using a deep net with respect to parameters phi, and this has to do that original parameters theta that we talked about. And we'll learn these parameters via backpropagation. We already saw backpropagation, and we also, Robert told you about the auto differentiation, essentially tools, computational tools that exist. So essentially, you can perform all of this in that fashion. And let me just briefly and rather quickly go through a few derivations. We want to optimize. Well, what is it that we want to optimize? What is the loss function? If you look at the log of this probability of x, the underlying distribution, this is something that I already wrote before. You can just, this is integrating with respect to z. This q sub phi log p theta, starting from the encoder block. And then I can expand this essentially using just writing the equivalent form of p theta of x, which is the ratio of these two. Why? Because p theta of z given x times p theta of x is equal to the joint distribution in the numerator. I've just expanded this, okay? The definition of the joint distribution with respect to conditional distribution. And then I can take the log and then just add the following, divide both sides by this term, p sub theta of z over x, okay? And if I do this, the reason why I'm doing this, by the way, is it's not just algebra gymnastics. It's you'll see in a minute why. And then I can break this integral into two parts. The part that has essentially a term that is a function of this joint distribution p theta, and the q, which was the conditional model for our encoder. Okay, the product of these two. And similarly here, this is a function of q of phi, but p of theta, which is a function of essentially conditional distribution of z given x. these two have names, the specific names. It's beyond the scope of what we need to worry about, but this essentially corresponds to a D sub KL that's known as a KL divergence. Okay, has anyone heard of that term before? Yeah, okay, so that corresponds to a KL divergence, which is essentially a measure that's non-negative, okay? And then we have this L, which is referred to as the empirical lower bound, or elbow, okay? And what's the significance of this? Significance of this is that, remember, we want to minimize negative log likelihood, right? And this quantity is always greater than or equal to L. Why? Because this is never negative. It's either 0 or 1. If it's 0, that means the two parameterizations, phi and theta, are exactly the same. So this is going to be always the same. If we're going to search for the minimum, then we only need to worry about this. This essentially puts a bound in what our optimization needs to work with. Okay. All right. So anyway, let me just step through these in the interest of time. I basically, through some few steps in math, we can recognize that what we have is this translates the second term into an expectation value of this conditional log of probability of the data given the latent variables. And this is really the reconstruction of, this corresponds, that expectation is the reconstruction of the samples from that distribution. This has the notion of a regularization. Remember, we had a regularization, which was the form of the norm of the weights in the discriminative model. And this is essentially the corresponding case in the generative model. Okay, that's the form of the regularization. And this is the reconstruction. It's just breaking those two things. And what we are seeing over here is that we can approximate that expectation operator by just looking at essentially sampling this log of p theta of x given zi. This goes back to what I started with, saying that I don't want to just sample z. I want to find likely z's that are more likely to give me the distribution, be related to the underlying distribution that I want. And that's precisely what that second step does over here. So in practice, what are we talking about is you have something like this. This is your data you want to learn. You want to learn the structure using variational autoencoder. And you basically get samples of log of p theta of x given z1 all the way to zn. And typically n is small, so it could be just one latent variable. In the examples I showed you in the original paper, they only had two z's, two latent variables. Okay, how to back propagate through the sampling step? We essentially, this z is from the Q. We assume that this is Gaussian, and we have the mean and the variance. And there's a parameterization that allows us to be able to essentially perform this using this common architecture, a deep net. And that parameterization essentially allows us to have this sigma, which is Gaussian, that's injected into the latent variable or the hidden variable. And then we can just jointly construct this deep net for this task. Okay, that's the diagram. I won't go through the details. We've already gone through the details, and I showed you the results. So in the interest of time, I'm going to move on and talk about the next topic, which is generative adversarial nets. Are there any questions before I move on, or comments? Backpropagation, let me go back to that slide. Backpropagation means that, remember, basically we need to find these parameters theta to draw with these, and we need to find, so we want to generate, this is what we want to generate. So the standard example you can think of is that you have a bunch of, let's say, faces, images, okay? And you want to generate new faces from those distributions. So these x1 and x2 will be different than what the data saw. But the underlying assumption is that they come from the same distribution. And by the way, I don't know, those of you who follow the news related to what is happening with generative AI, last month for the first time, the Vogue magazine had pictures of models that were entirely generated in ways that I'm describing to you. It was not a human model. It was a big deal. It was for the first time. There was a lot of press because of it. But that's what I'm talking about. So you train, you generate some data, and then you draw new data, variations on that. But back propagation means that I need to optimize parameters theta and phi, which means that I need to compute the derivatives and sequentially pass those derivatives in order to be able to use some optimization, some search for the minimum, such as a gradient descent or a stochastic gradient descent. That's what that means. Okay, is that clear? Yes. Yes, 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 yes. Exactly, except that we don't do it in sequential ways. It's the architecture does exactly what you said, but we are basically optimizing both theta and phi. Any other questions or comments? Okay, so let me talk about the next idea, because the next idea is somewhat of a departure. The third part of what I want to talk about is similar. It's basically taking what we talked to almost the next level of sophistications. That's the diffusion models. But first, I want to talk about an idea that's a departure from what we just saw. And let me explain to you in what way it's a departure. These are the references for this part. And the main idea is don't write a formula for P of X, the same way that we wrote it in terms of a likelihood, okay? Just learn to sample directly, same way that we were drawing the samples X. So we don't have a summation over large probability spaces. The way we had the summations, we had to compute these likelihoods and the conditional densities, right? So what does that mean? That means that we formulate the problem as a game, a competitive game, between two players. So it borrows from some ideas from game theory, which the two-player game has, one of them is a generator. We will denote that by G. And then another player is what we'll denote by D. That's a discriminator. Okay? And they're competing. Just keep that in mind. And what do I mean by that? I mean, the task of the player G is to generate samples. Okay? Not from data, but somehow generate samples, maybe artificially. And D, the discriminator, predicts whether the sample is artificial or real. Okay? So D has access to some XIs, real data. Okay? Generator doesn't. Generator is artificially pumping out these samples. Okay? And then the discriminator is supposed to say, is it real or am I being tricked? Is it real or am I being tricked for each one of those samples? So it operates on each sample, sample by sample. So G tries to trick D by generating samples that are hard to distinguish from the data from XIs that we have access to. So the goal of G is to generate realistic samples, even though they're artificially generated. And the goal of D is to tell them apart. Okay? And this is the block representation of exactly what I described to you in words. Let's start from this part, this building block. So what we start with, by the way, the right is what? Is the generator block. The left is the discriminator block. Okay? So the generator block is, you start, again, the only thing that you see in common from the variational autoencoder is that we are drawing samples X1 and X2 from some arbitrary distribution, typically a Gaussian. And we learned, so this exactly corresponds to which block of the variational autoencoder? Which one of the two blocks is this? The decoder. The decoder has basically generate samples, suppose samples from noise, from Gaussian, and then draw samples X1 and X2. And you remember what we said, how we learned this, okay? We learned the function relating that. from that latent space to something that has structure, x1 and x2. And so what does that mean? That means that we input samples from the distributions, and we have a differentiable function g in between that we use backpropagation and everything that we have learned so far about deep nets to draw samples g. Artificial sample, we call that g of z because generator is drawing things from z. And then we have another differentiable function d, that's the discriminator. And this discriminator tries to predict z. That's its job. It may not be able to do that every time, but the goal is to try to predict 0, which means that this is an artificial sample. It's not real. On this side, we have data. This is like real images, right? That's the data that we are trying to learn a distribution from. These are samples of the data that, again, this goes through a differentiable function d. Look at what this looks like. This looks like which block of the variational autoencoder. Exactly. So we have these samples from the data, and then it's not exactly generating noise like the encoder part of variational autoencoder, but it generates a binary class. Is it authentic or is it artificial? Is it authentic or is it artificial? Okay, each time the sample comes in. So is it clear conceptually what the idea is? Okay, so the next step is, how do we map this to a computational problem? We have to set it up and solve for this. Any ideas about how to do that? What should the cost function be? But when I say computation, by now I think we see the pattern. You have to define some sort of a loss function or cost function, and then you have to search it using some optimization approach. What should that loss function be, in your opinion? It may have some semblance of that later, but just basically think about it in terms of, there are two, right? There are two tasks. Let's start with, for example, the discriminator. What should the cost, the loss function for the discriminator be? And then we talk about generator. In terms of the parameters that we have, which is probability of the data, xi, right? Yes, you want to, again, the optimization is that we want to find parameters, right? That's what we are doing. We want to find the parameters of this that optimizes our classification. We want to have the best classification. We want to find parameters here such that we come up with the best classification task, just like we had in the last lecture, okay? So let's see how we can write it. Look at the first line. What does that mean? We want to minimize a loss with respect to parameters w. So first of all, generator is g, discriminator is d. Discriminator was the block on the left, okay? With respect to parameters w, which is what? It is probability of y equal 1 if x. If the data is authentic, we want to essentially attach it to label 1, assigning that, declaring that it's real. Otherwise, it's 0, okay? So we want to minimize with respect to parameters w that we are learning from the deep net a negative log of dw of x, which is this, okay, minus, what am I writing over here? Anyone recognize what I'm writing over here? It's a binary classification, so essentially it's a Bernoulli. So I want to write two terms, one for probability of when we have the real images or real data. And the next one is the probability of when we have artificial, right? Which is probability of y equals 0 given x. But probability of y equals 0 given x, because it's binary, is equal to 1 minus probability of y equal 1 given x, because it's Bernoulli, okay? In other words, I can write that, I'm just writing it in one step. 1 minus the probability of it being the class 1. So the sum of these two terms, but one is with respect to x, the other one is with respect to z, because why? Because this discriminator in this case is operating not on real data and not on x's, but on the output of the generator, g theta of z. Okay? All good? So that's the goal of how we would choose the parameters w's for the discriminator. What is the overall cost? What should the overall cost be? Well, it's written, but does it make sense? What are we talking about? We are saying that now we want to choose theta, theta being the parameters of, let me show you what, these are theta, right? The parameters of this. We want to choose theta in the essentially the decoder block, such that what cost is maximized? Well, we want to maximize theta because remember, this is a competitive game. This is essentially what we call a non-cooperative game, right? So because the two players want to beat each other, that means that we want to maximize theta for the cost that's up here, which is the cost of the discriminator. We want to find theta that maximizes essentially the cost that we had for the discriminator. Okay? So what you're seeing over here is essentially the entire form of the cost of a generative adversarial network or a GAN. And the rest of it has to do with how do we compute that. That's the idea. And I'll tell you a little bit about the ideas for how we compute it without going into all of the nitty-gritty details. The idea is that, of course, as you can see from the form of what we have, a max-min function, there's a minimum, there's a maximum with respect to that. And there are two different parameters. Essentially, what we would do, you could think of this is what's referred to as an alternating optimization. Okay? An alternating optimization problem, which means that you alternate over two optimization problems to find the optimum of the first one, and then you go to the second one, and then you repeat that. So the first step is a gradient step with respect to W. Okay, W, again, as a reminder, are the parameters of the discriminator deep net. The second is a gradient with respect to theta, which is that decoder block in our generator. Okay? And then in practice, there are heuristics that make this optimization more stable. Go ahead. So oftentimes we have, remember this is what, by the way, I referred to in the previous lecture as the cross entropy cost. Cross entropy means negative log likelihood. So that's basically, and oftentimes we change those with just essentially a sign. So it's a log. Oh, you mean the cost? Yeah. So basically, all we're saying is that the negative log comes about as a result of the fact that, you remember, in the discriminative case, we are exponentiating something, and we had the negative, similar to the way you have the negative in the form of the Gaussian. It just comes from, typically you have that capital F, the score function is exponentiated, and then that's why we take the log. Another reason is because we are looking at essentially not a single random variable, but a product of them with the IID assumption, and then we convert that product of joint distributions in higher dimensions into a sum. Okay, so let's look at this briefly. What is the optimal discriminator, assuming, so this is, I want to talk about a little bit about how you compute this. This is the discriminator. We want to minimize D with respect to, now I'm writing it instead of summations in terms of integrals, because I want to relate this to some computation that's essentially available to us, the form that's available to us in other contexts to utilize. So it's probability of data of x log D of x integrated with respect to x. This is the first term in the previous picture, in this picture. I'm basically rewriting this in terms of an integral, and the second term is I'm rewriting this in terms of an integral, those two terms. Okay, and so basically just rewriting this in terms of an integral. And then the next thing I want to do is I want to combine this, because this integral is over z, the latent variables. This one is over data space x. I want to define everything over data space x. And I can do that. Why? Because as long as I know, so this probability is with respect to g, that generator, instead of z. Because just like the picture I showed you, you can always come up with a mapping. If you have random variables that you're drawing, it's essentially just the transformation of a random variable to another random variable. You draw samples, and you can map it to another probability space. Okay? And so that's exactly what we're doing here. And now everything is in terms of x. And now we want to come up with something that allows us to be able to minimize a form similar to this. You have essentially a loss function. This whole thing is a loss. Okay? That loss function is a function of the data x, and it's a function of d. And it may or may not have the derivative d. In this case, we don't have it. But there is a general formalism. This is actually, many of you may recognize this, right? It's actually the context in which this sort of integral needs to be optimized is physics, right? So Euler-Lagrange formalism, which basically has this S of d of this form. And we can find the stationary d by just setting, and what I'm writing over here is, I'm not showing you how you can go from an integral of this form to the solution, but you can just look it up, and the derivation is available to you. And we don't have the term with respect to d, so essentially just this is the form that we need to obtain and solve for computationally. And the optimal discriminator, assuming arbitrary capacity, ends up with to have a form that has that essentially a probability of data divided by probability of data plus probability of that generator with respect to data as its argument. Okay, that's the result that you get. But you can go through these derivations once and just make sure that you can compute these things. Of course, there are solvers that you can use, but it's good to just understand how they work, what the issues are. And I can also tell you that in practice, there are deviations from this optimal solution that work better for reasons that we won't get into today. Okay, again, some details about now what is the optimal generator. We can go through a similar analysis and write it in terms of what you said earlier. It should have a form similar to the KL divergence. And yes, the generator does have that form. This is about the heuristic that's important in practice. Again, just be aware of it so you can look it up, but I won't go over it. Okay, here's just one example on a toy example. You have the following. You start. This green is what the data that your, which one, G or D, starts with. I want to make sure that. So the green corresponds to the generator. Generator doesn't know. These are clusters in the data. The blue are data. They have structure. They have their clusters. The generator draws from noise and just drops these samples right there in the middle somewhere. And after 2,000 iterations, you can see that there's the following, right? So things become a little bit closer. It finds the cluster centers. There's still some spread, some more over here. And then eventually, after 5,000 iterations, it comes pretty close. Yes. I'll go back to the diagram because that's important. Your question is important. So what's given to us, remember, what is given to us and what is our goal? What is given to us is just a bunch of data, X samples. You can think of it as a bunch of time series, records of some event or some images. Okay, that's the only thing we have. And our goal is to end up with probability of X, a distribution of X from just samples. Now, of course, we are doing an approximation of that underlying distribution. The assumption is whenever you see some data, right, if I give you 200 images, let's say natural images, you know that they are drawn from an underlying distribution, but we don't have access to that distribution. So the whole idea of generative AI, generative machine learning, is to somehow learn that underlying distribution, to approximate that. But all we have is just these samples. And the way we approximate what that distribution is, because if we have that approximated distribution, now we can draw more samples from it, right? So what you're seeing in the diagram that I showed you, all of those greens, now essentially your GAN is just drawing samples from the distribution that it has learned, compared with the blue, which are the data that we are starting with. In the context of images, artificial, let's say, face images being generated, like don't correspond to anyone's face, but they're still can be indistinguishable from human face. That means that the faces are generated in a distribution from those green dots, and you can see some of them might actually not have much to do with our data XIs. They're different. They don't have to be the same because we don't know what the underlying distribution is. All we know is that we have samples of that underlying distribution being the blue dots. Does that make sense? Exactly, exactly. Yeah, our generator is what now is pumping out data that we believe is coming out of that underlying distribution. So eventually, more believable. That's the generated data, okay? Very good. So I want to transition now to the last part. These are some examples from those papers. The last part is the more recent advancement, the more recent development. It's known as diffusion models or diffusion-based generative AI. I'll talk about this briefly. There are some references. This one, as you can see, just because it's a newer concept, most of the papers are in the last 5 years, 3, 4 years. Okay? So what's the idea? We go back again to case that we have some sample data. This is a record of the data we want to work with. And again, the assumption is that XIs are drawn from an underlying distribution to which we have no access. And we will model the likelihood function as we did in the previous cases with some parameter theta, which again, it's an exponential of some negative of score with a normalization function. We saw this, we started with this before. We've seen it also in previous contexts. Sometimes in physics, that normalization is referred to as a partition function. Okay. So the difficulty is that, in fact, we saw this in the case of variational autoencoders. It's not tractable. So this z theta is normalizing constant. The role of it is to just ensure that this is a proper probability. It integrates, the whole thing integrates to 1. And we want to maximize this log of probability theta of x over the data record of n data points or data vectors. And we have this intractable normalizing constant computation, this z, okay? And so we want to be able to deal with that issue. And the idea, again, the central idea for each one of these, if you were to remember, this is the slide that tells you the central idea before I go through the details of the mechanics. The central idea is that instead of going and working with the log of probability, okay, instead of that, work with the gradient of the log of probability. So that's the difference between all the previous generative models that we saw versus the diffusion-based model. The diffusion-based model operates on the gradient of the log probability rather than the log probability itself. Why does it do that? Of course, there has to be motivation for that. The motivation is that you can see from these few lines that you can bypass the calculation of that normalizing step. So the idea is what? So we work with the gradient of the log, then we learn something that's known as a score function. That score function is with respect to parameters theta, and it operates on the data that we have. And we want to make it approximate to this log, the gradient of the log of probability. So we want to learn a score function S so that it approximates this quantity. And if you look at that S and just write it, if it's close to the expression I have up here, it becomes a negative gradient of the function, the score function F, minus the gradient of log of this Z, the normalizing function. I'm just writing out the ratio of log because we have the log. If you just go back here, all I'm saying is that here, I'll just expand this when I take the log. You have the numerator, denominator. I'm just writing it out. And you have this negative term here. And we are differentiating with respect to parameters theta. This is x. And essentially, this term, log of z theta, okay, since this has to do with x, essentially drops out. We don't need to compute that anymore. So that's the advantage of going from working with log likelihoods, instead of that, working with the gradient of log likelihoods. And that's really the underlying idea behind diffusion models. Okay, so how to learn the score function? We want to learn an expected value, an expectation with respect to probability, the underlying probability distribution, by minimizing with respect to finding parameter thetas that minimizes the expectation of the difference between the score and the gradient of log probability in some, let's say, L2 norm or some distance, Euclidean distance in this case. And we use techniques known as score matching to solve it and estimate the parameters directly on the data set using stochastic gradient descent. So suppose we have done that. Now we have estimated the underlying probability distribution, and I want to draw samples from that probability distribution. And an idea, again, having its roots in physics, in thermodynamics, is what's known as Langevin dynamics. Okay. Langevin dynamics essentially implies that, what is it? So we have the score function, which is now approximating our gradient of log probability. It is trained after we have done the score matching. We have made that minimization of the expected value. It's an iterative process that can be used to draw samples from underlying distribution that we have learned. So we have learned probability of X, the distribution, but now we want to generate. This is the generation part. Generate samples from it, okay? And what Langevin dynamics essentially implies is that we can draw samples recursively, iteratively, sequentially, by essentially taking the previous sample with some parameter and look at the gradient of the log px plus a term that has to do with noise. Okay, this is the perturbation term. You perturb that original distribution. And that perturbation, essentially what we're talking about here is that this x0 is some arbitrary prior distribution. Zi's are zero mean unit normal distributions. And then this, you can think of it as a perturbation around the first sample that we started with and something that has to do with essentially our underlying distribution. And when epsilon goes to 0, so this is a result that I'm just stating, but there are proofs of these results, is that as epsilon goes to 0, so this essentially, the limiting case is modeled by a stochastic differential equation. As epsilon goes to 0 and the number of iterations in Langevin dynamics gets larger, you can actually show that the samples that you draw, x sub k's, are according to the underlying distribution probability of x, which is quite powerful, right? All right, so let me show you, just in the remaining 5-10 minutes that we have, a little bit of the issues that we need to be aware of if you want to work with this underlying model. The first issue is that for this score-based generative modeling, what you're seeing over here on the left is an example of data samples. Just imagine that in this space is this space of the underlying distribution from which you want to learn your distribution. In this case, for example, some images. Okay, so you have all these data points over here in your distribution. Some of them, if you think about that sum distribution, so not all of them are centered at the mean. There's some variance, some spread. And essentially what I'm showing over here, maybe there's a cluster here, maybe there's a cluster here. And remember, score matching is, again, as a reminder, let me show you. Score matching corresponds to the following task. This minimization problem, okay? After score matching, if you, for example, look at the errors, you're minimizing, right, that cost, the difference, you'll see that your cost, essentially your match is very good in the areas where you have data, parts of the distribution that you have data, you can see parts of that distribution better, and here, but the parts of the distribution from which you don't have access to data, you have a larger discrepancy, okay, in your score matching. And of course, at this point, you want to draw samples to generate new samples using, for example, this Langevin dynamics. But this is going to give you some errors because of this. Your distribution that you're approximating is not as good as it can be. And the idea behind these score-based diffusion models is to modify this picture somehow so that your errors are distributed more evenly everywhere. And the idea there is the following. Suppose you have some data density that most of the concentration is this part, maybe a little bit this part. Less accurate score estimation for less densely populated areas. So we have worse score over here, inaccurate in the red areas. Okay? And the idea behind diffusion models is that you perturb data points with noise and train score-based models on the noisy data points. In other words, if I add noise to this picture, this is what I get. There's a spread. You add noise, and now what I have over here is essentially something that looks like a better problem because the amount of areas in the distribution that I had no information from now is smaller. I've spread whatever samples I had over here by just adding noise to this process so that I have a better handle on the distribution. And of course, just like everything in science and engineering, by doing that, I have modified whatever that underlying distribution was. So there's a trade-off. Okay, but the idea is that we want to cover low density regions, but we don't want the noise to be so large to alter the original data distribution. So what does this look like? What it looks like is that we use multiple scales of noise. Instead of doing just one noise, we actually do this at multiple scales of noise. Less noise, more and more and more, in order to be able to essentially do these noise perturbation, not in a way that will modify our distribution so much, but at the same time, give us a better estimate of the distribution. And this is the original image. You end up with a noisy version of that. Essentially, just all you have to do is your probability becomes a function of some noise variance. And that noise, for example, could be a Gaussian noise with variance sigma squared. And you're integrating with respect to the parameters. So then you train a noise conditional score-based model. So your score-based is now conditional based on different values, scales of noise. And after training, we produce samples using annealed Langevin dynamics. Essentially, you go back and you do the Langevin dynamics, but you are annealing different levels of noisy samples. And this model in a sequential way. So noise scales as L goes to infinity. So this is basically a model that what I'm showing to you over here. It models a stochastic differential equation. Okay, basically, we all know about ODEs, differential equations, and the stochastic version of that. So this is the ODE part, right? And the stochastic part, all it means is that now you have another function which adds the noise, the perturbation to that ODE, where W is a standard Brownian motion, so the integral of white Gaussian noise. dW is some small white Gaussian noise. And G of T are known as diffusion coefficients. And we can obtain higher quality samples. And there are other attributes, properties that are desirable. But essentially what that means is now that we have the reverse stochastic differential equation, where we can obtain, so from here starting to X of T, and then there is an expression that has to do with the score function, and we can go from X of T back to the original set of samples that we want to draw. This is known as the reverse SDE, stochastic differential equation. And we train time-dependent scores based on that model. I'm just going to speed up a little bit in the interest of time. We have about 5 minutes. So how to solve the reverse SDE? There are numerical SDE solvers. Of course, stochastic differential equations this is not the only place they appear. They appear in a whole range of different problems in mathematical physics. And this is the process of reverse diffusion sampling. And typically we use, in a very similar way that we just saw, the predictor corrector. This is this alternating optimization to generate high qualities. I'll skip over the details of the variations on how you would do the sampling. I want to show you a result on something that my group has been working on. And the idea here is essentially to show the forward and reverse process for the multi-channel parameterization of a data cube for a computational spectral imaging concept that allows you to do instantaneous or snapshot imaging. And but it requires solving an inverse problem. And the inverse problem is solved using this diffusion model. So we have 3 parameters we want to solve. There is intensity, velocity in this row, and the line width. And these are images that are actually taken from samples from Hinode ICE instrument. And you can pass it through this formal SDE, which takes the data, brings it to noise for each one of those parameters, the 3 parameters. And then through a sampling, some posterior sampling, it generates the original. So now we can essentially learn where does it come from in the context of solving an inverse problem for us. Now we can generate priors. Remember, in a Bayesian inverse problem, probability of X is something that we assumed in the 2 lectures ago for it to be either, for example, smooth, an L1 norm, L2 norm. But this is a way for us where we can actually learn that from the data directly, rather than specifying some just a generic mathematical form to it. So it's a learned prior. That's basically what I'm talking about. I can skip this. This is some theoretical results showing that it actually does give you the correct ODE. So in summary about this, score-based models learn the gradient of log density of the data distribution, and diffusion models gradually add noise to data. That's the forward process, and learn to reverse this process. And it's powerful for generative modeling because we can sample from complex high-dimensional distributions. Incidentally, remember what we started with, variational autoencoder. We went from data to Z. Z was noise. And we went from noise to draw samples. You can see the pattern, right? The similarity over here. The similarity, except that the model is slightly different. It's actually broader than that, right? But it's the exact same idea. Okay, and of course, I already mentioned that we can use this as learning priors, data-driven priors for inverse problems. Okay, so it enables conditional sampling. I already talked about the idea of if we have an inverse problem and we want to sample from the posterior, this allows us a powerful way to do that. And I've already talked about the steps. So let me, in a few minutes that I have, this is, by the way, just some results of the similar experiments that I talked to you about. These are the spectral orders, the parameters, intensity, velocity, line width, posterior samples at different levels, posterior mean. These are essentially the different samples of the posterior, the mean, the sample. And it generates multiple plausible reconstructions. What I'm showing you over here, which is an important point that if you work in this area, you need to be aware of, is the topic of distribution shifts. So the question is, how robust is this learning engine, generative learning engine that you have developed, if you're drawing samples from that distribution or drawing samples that are completely different than the distribution that you just learned through this diffusion process? This is an example of out of distribution. So clearly, you have things that are very different that are learned from that original one. And if you compare it with the standard unit structure as opposed to what we showed you we developed in the diffusion model, you can see here that you end up losing a lot of information. Here you're able to, in this case, compare this box with this box for the case of intensity. So it really allows you to be robust to distribution shifts. Okay. I want to just, because I started 5 minutes late, let me just tell you one final thing that has to do with linking concepts, fundamental concepts we learned about generative machine learning methods to essentially a lot of things that you see around yourself, because those things, whether it be large language models, transformers, foundation models, how do they connect? What's missing from our discussion, and I'm just going to allude to it, is that we need more flexibility regarding inputs and outputs. Sometimes when you type some text with a pre-trained generative model, which is, for example, a GPT, the text comes, or if it's a translation, it's a sequence of data. You don't have the data just looking at the one vector of data, right? And so that we have sequence of inputs and sequence of outputs, and the length of sequences may vary. And so you can imagine that instead of just the standard architecture that we have, these are building blocks with deep nets, you can have one-to-many, many-to-one, many-to-many, and many-to-many with some essentially latency. And so sequence of models are, of course, there's a lot of literature and work on modeling such things with essentially time-dependent aspect of these sequence of data, including things such as recurrent neural nets, long short-term memory, or LSTM, gated recurrent unit. I'm just mentioning this so that I'm not going to talk about them, but just that so you're aware that there is variations on this theme that can really enable a lot of the technology that you see around. So recurrent neural networks, for example, captures this notion of dependence on time. Okay, that's the model that you have. Of course, it has many applications in natural language processing, speech recognition, image processing, video processing. And the general structure for recurrence can be written in terms of something that looks very similar to that dynamical model that I wanted to get to in that first lecture. And transformers, again, transformer is that you have a set of input vectors. At the output, again, you have a set of outputs. And the computation requires something that has the notion of self-interaction and some normalization layer and some position of normalizations that may change. And it has something known as a self-attention. So attention is a concept in terms of how you can design these architectures. And it has something known as an attention. The idea is it has, we all know, we have all used it. It has revolutionized language, natural language processing. You just download a lot of text. Okay, that's the pre-trained part. You train a giant transformer model, and then you fine-tune on desired task with little new data coming in. That's really the idea behind it. And of course, all of these things we are talking about, pre-trained, okay? So that's P in GPT is the pre-trained. So the standard rendition, formulation of it works really well for things that are already pre-trained. But if you come up, for example, if you play the game, some of you know the game Hangman. If you play that with a GPT, it does not perform well because it needs to adaptively change its strategy and the knowledge that it has to be able to adapt to. It's pre-trained, remember? So that's, but of course, these developments are all happening. There's a lot of other developments in this space. For example, dynamic programming, reinforcement learning, all of those concepts apply to the case where we want to do things dynamically rather than just static. Okay, I'll stop here and thank you for your attention. Yeah, that's a good question, and there are. The answer is yes and yes. So it goes back to this picture. Maybe I should show you that picture real quick. The picture that has to do with the original, this picture. So the amount of noise has to do with going from something like this to that. And of course, we do this at scales, right? We don't just go to no noise to a lot of noise. In fact, that's the model of the stochastic differential equation. It adds noise at different scales. So the trade-off, the implications that you're asking about is that if you have too much noise, your score matching is going to be more accurate. I mean, if you compare noise and noise, You can fit noise to noise, no problem, right? The problem is that at that point, you don't have any information about the underlying distribution. So the trade space is that you want to add enough noise so that hopefully you get information from other unseen parts of the distribution without washing out your underlying distribution. So that's the trade-off that I have to, of course, what does it mean? The implication is that it has to do with the amount of data you have. Is your data representative? So not the training, but the data that you start with to essentially build your generator. I mean, if you have very little data, if you just have 10 samples of something, how well can you approximate your distribution? So that ultimately boils down to that. So you develop those kinds of, I mean, you can develop intuitions, but there are also methods by which you can, there are methods to, by the way, something that I haven't talked about at all, which is an entire subject with books on it, is what's known as statistical learning theory, which has to do with essentially putting bounds on the performance of your machine learning algorithms. Some of those bounds are useful, but some of them are very theoretical and may not apply to the specific cases that we have. But so there are methods for getting some insight, but intuition is also important, right? Just like all of these problems that we work on. Yes. That's a great question. It's probably, I mean, and it's a deep question. The notion of entropy in statistical physics is what was generalized to the notion of entropy in information theory by Claude Shannon. In the context of information, first of all, you have to quantify what do we mean by information. And he was developing these ideas in his 1948 paper in the context of information transmission. You have an input set of information that you essentially, you can quantize it in bits, and you have a channel through which you transmit that information, and then you want to receive it. So of course he was interested in the capacity of that channel and all of that. So the notion of entropy in statistical physics was what was used for him. I mean, the same notion of disorder, right? So you have the negative, you have the sum or integral, negative log of p times p. That's basically what you're looking at. And if you just go through the probabilistic range of values that you can get, if you essentially use numbers, for example, entropy of a set of images, it just means the amount of the lack of information. So you can interpret it as lack of information. So conceptually, they're the same concepts. And if you actually work out what numbers mean in the probabilistic model and in the statistical model, they essentially capture the same thing. One corresponds to a physical system, and the other one corresponds to quantifying the notion of how much we know something, information. And that's the context in which, when you see KL divergence, when you see essentially the cost for all of these things is what's called a cross entropy. When we talk about negative log likelihood, that is essentially just a cross entropy cost. It's essentially the reverse of the information, what we know about something. It's lack of information. That's the way you can think of it. So
can you repeat the question?
Yeah, the question is, for the diffusion model, if instead of starting with clean samples, I have noisy samples, what's the implication for this model, and can that allow me to clean the noise from those samples? And the samples that you have, your data, the only way you would be able to tell if they're noisy or they're not noisy is if you knew the underlying distribution from which they're drawn. If you did not know that, if you did not know what the underlying distribution was, you may get an image with salt and pepper noise and say that, well, this looks noisy to me. It looks to human eye as being noisy. It has this perturbation. But maybe that is the distribution from which all of these data is being generated. Maybe your instrument is generating those, and that's real. Real meaning in the sense of maybe not smooth to the human eye, but it may be coming from the underlying distribution. Okay, so the decision of what is signal and what is noise, sometimes it can be made arbitrarily, subjectively by us, or you can assume that it's coming from a distribution that you don't have access to, but all you have are those samples. And then you work with those samples, and then you essentially build this stochastic differential equation model to just generate. The whole idea is that whatever your underlying distribution gave you those samples, you build a machine that you can generate from that same distribution, whatever that may be. Noisy, embedded in it, or not noisy. But if your goal is to eliminate noise that you're guaranteed, you're convinced, you're certain it's noise, there's of course denoising. Application of removing noise is one of the most classical and well-studied problems in signal processing. So I can certainly point you to a lot of those ideas. In fact, denoising, machine learning has recently played a role on state-of-the-art denoising ways of solving that problem, but it's a classical problem.